In the vast expanse of space and time, stretching beyond the reach of our most powerful telescopes, lies perhaps the most profound question humanity has ever dared to ask. Not how did everything begin, but how will everything end? Tonight, we embark on a journey through cosmic time, exploring the ultimate fate that awaits our universe, examining the scientific theories that attempt to answer this most fundamental of mysteries. The universe around us appears eternal and unchanging from our brief human perspective. Stars shine steadily in their constellations, galaxies spiral majestically through space, and the cosmic dance continues as it has for billions of years. Yet beneath this apparent stability lies a deeper truth that modern astronomy has revealed. The universe is not static. It changes, evolves, and moves inexorably towards some distant, ultimate conclusion. Four major scenarios emerge from our current understanding of physics and cosmology. Each tells a different story about the final chapter of existence itself. The heat-death scenario envisions a universe that gradually cools and expands until all energy is evenly distributed and no more work can be done. The Big Crunch proposes that gravity will eventually overcome expansion, pulling everything back together in a cosmic collapse. The Big Rip suggests that dark energy will accelerate expansion so dramatically that the very fabric of space-time itself will tear apart. And the cyclic models propose that our universe may be just one in an endless series of cosmic births and deaths, expanding and contracting in an eternal rhythm. To understand these possibilities, we must first appreciate the immense scales of time and space we are contemplating. The universe is approximately 13.8 billion years old. This seems impossibly ancient from our human perspective, yet in cosmic terms, this represents merely the earliest moments of what may be an incomprehensibly long story. The scenarios we will explore unfold across timescales that make the current age of the universe seem like the first microseconds of a day that stretches for millions of years. Consider the stars that illuminate our night sky. Each one represents a massive nuclear furnace, converting hydrogen into helium and releasing tremendous amounts of energy in the process. This stellar burning cannot continue forever. Every star has a finite fuel supply, and when that fuel is exhausted, the star must die. The manner of death depends on the star's mass, but death is inevitable for all of them. The smallest stars, the red dwarfs, burn their fuel so slowly that they can continue shining for trillions of years. These dim, cool stars will be the last lights in the universe, their feeble glow persisting long after our sun and all the bright stars we see today have faded to darkness. But even they must eventually exhaust their nuclear fuel and fade away, leaving behind cold, dark remnants. More massive stars burn through their fuel much more quickly, living fast and dying young in cosmic terms. Our own Sun, a medium-sized star, will continue burning for approximately another 5 billion years before it begins its death throes. As it exhausts the hydrogen in its core, it will expand into a red giant, possibly engulfing the inner planets, including Earth. Eventually, it will shed its outer layers and collapse into a white dwarf, a dense, hot remnant that will cool slowly over many billions of years. The most massive stars end their lives in spectacular supernova explosions, leaving behind either neutron stars or black holes. These dramatic deaths temporarily outshine entire galaxies, but they too represent endings rather than beginnings. The neutron stars will gradually cool and fade, while the black holes will slowly evaporate through a process called Hawking radiation, though this process takes an almost unimaginable amount of time. As we contemplate these stellar deaths on the largest scales, we begin to see the first hints of the heat death scenario. This theory, rooted in the second law of thermodynamics, suggests that the universe is moving inexorably toward a state of maximum entropy, where all energy is evenly distributed and no more work can be done. Entropy, often described as a measure of disorder, always increases in isolated systems. The universe as a whole can be considered an isolated system, meaning that its total entropy must always increase over time. This fundamental principle has profound implications for the ultimate fate of everything we observe. In the early universe, matter and energy were highly concentrated and organized. Stars formed from gravitational collapse, creating regions of high energy density surrounded by relatively empty space. This organization allowed for the complex processes that created heavier elements, planets, and eventually life itself. But every process that occurs, from stellar fusion to the formation of black holes, increases the total entropy of the universe. As entropy increases, the universe becomes more uniform and less capable of supporting the organized structures and processes that characterize the cosmos we observe today. Temperature differences that drive stellar processes gradually even out. The organized matter in stars and planets slowly disperses into space. The universe becomes increasingly uniform and featureless. This process occurs over timescales that dwarf the current age of the universe. The era of star formation, which we are living through now, will continue for approximately another 1 trillion years. During this time, new stars will continue to form from the gas and dust scattered throughout space by dying stars. But the supply of this raw material is finite, and eventually, no new stars will be born. After the last star formation has ceased, the universe will enter what cosmologists call the stelliferous era's twilight. The remaining stars will continue to burn, but their numbers will steadily decrease as they exhaust their fuel and die. Red dwarf stars with their incredibly slow burn rates will dominate this era, providing the only sources of energy and light in an increasingly dark universe. As these final stars slowly fade, the temperature of the universe continues to drop. The cosmic microwave background radiation, the afterglow of the Big Bang, grows ever cooler as the universe expands. Space becomes increasingly empty and cold, approaching absolute zero. Even after all the stars have died, the universe will not be completely uniform. Gravity will continue to act on the remaining matter, slowly drawing it together into ever larger structures. Brown dwarf stars, planets, asteroids, and other debris will gradually spiral into black holes through gravitational interactions and radiation. These processes occur extremely slowly, taking far longer than the current age of the universe. Black holes, the final repositories of organized matter, represent the last bastions of non-uniform energy distribution in the universe. But even these seemingly eternal objects are not permanent. Stephen Hawking showed that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly evaporate. The evaporation rate is inversely related to the black hole's mass. Smaller black holes evaporate quickly, while supermassive black holes take an almost incomprehensible amount of time to disappear completely. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to evaporate completely. Supermassive black holes containing billions of solar masses would take even longer. During this era of black hole evaporation, these objects will be the only sources of energy in the universe. The Hawking radiation they emit provides a final, feeble source of light and heat in an otherwise cold and dark cosmos. As each black hole finally evaporates completely, it releases its remaining mass as a brief flash of radiation before disappearing forever. After the last black hole has evaporated, the universe will consist primarily of elementary particles scattered thinly throughout space. Electrons, positrons, neutrinos, and photons will drift through an ever-expanding void. The temperature will be essentially absolute zero, and no organized structures or processes will be possible. This is the heat death scenario in its most complete form. The universe continues to exist, but it is a universe devoid of complexity, structure, or change. Maximum entropy has been achieved, and no further evolution is possible. Time effectively becomes meaningless, as there are no processes or changes to mark its passage. Yet even in this seemingly final state, quantum mechanics suggests that extremely rare fluctuations might still occur. Over timescales so vast that they make the age of our current universe seem infinitesimal, random quantum fluctuations might occasionally organize matter and energy into more complex structures. Some physicists have speculated that these fluctuations could even give rise to new universes or new regions of organized matter, but such events would be separated by intervals of time beyond human JAF. Comprehension. The heat death scenario assumes that the expansion of the universe will continue forever, growing ever cooler and more dilute. But this assumption rests on our current understanding of dark energy, the mysterious force that appears to be accelerating the universe's expansion. If dark energy behaves differently than we currently believe, the fate of the universe might be quite different. This brings us to the second major scenario for the universe's end, the Big Crunch. This theory suggests that the expansion of the universe might eventually slow, stop, and reverse, leading to a cosmic collapse that would destroy everything in a catastrophic compression. The Big Crunch scenario depends on the total amount of matter and energy in the universe. If there is enough matter, its gravitational attraction could eventually overcome the expansion of space itself. The universe would reach a maximum size and then begin contracting, pulling all matter and energy back together. As the universe contracts, the processes that occurred during expansion would reverse, but not in a symmetrical way. The cosmic microwave background radiation would gradually increase in temperature as space compressed. Stars and galaxies would be drawn together by the accelerating collapse, eventually merging into larger and larger structures. The final stages of a Big Crunch would be dramatic and violent. As space continued to shrink, the temperature and density would increase rapidly. Stars would be disrupted by tidal forces long before they could collide. The cosmic microwave background would become so hot that it would vaporize any remaining solid matter. Eventually, even atomic nuclei would be torn apart by the extreme conditions. In the final moments before the Big Crunch reaches its conclusion, all matter and energy would be compressed into an infinitely dense point, similar to the singularity that is theorized to have existed at the moment of the Big Bang. This would represent the complete destruction of everything that exists, as space and time themselves would cease to have meaning. Current observations suggest that the Big Crunch scenario is unlikely. The expansion of the universe appears to be accelerating rather than slowing down, indicating that dark energy is stronger than the gravitational attraction of all the matter in the universe. However, our understanding of dark energy is still limited, and it is possible that its properties could change over cosmic time. If dark energy weakens or reverses its effect, the Big Crunch could still occur, though probably not for many billions of years in the future. Some theoretical models suggest that dark energy might be cyclical, growing stronger and weaker over cosmic time, which could lead to a universe that expands and contracts in a regular rhythm. This possibility leads to the third major scenario, the Big Rip. In this theory, dark energy continues to accelerate the expansion of the universe at an ever-increasing rate. Eventually, this acceleration becomes so extreme that it overcomes not only gravity, but also the fundamental forces that hold matter together. The Big Rip scenario begins with the same accelerating expansion we observe today. Dark energy, which currently dominates the universe's energy budget, continues to grow stronger over time. This increased strength causes the expansion of space to accelerate more and more rapidly. Initially, this accelerated expansion affects only the largest scales. Galaxy clusters, which are loosely bound by gravity, begin to separate from each other more quickly. The distances between these massive structures grow at an ever-increasing rate, making the observable universe appear to shrink from the perspective of any particular observer. As the expansion continues to accelerate, smaller structures begin to be affected. Individual galaxies within clusters start to separate, no longer held together by their mutual gravitational attraction. The Milky Way and Andromeda galaxies, which are currently approaching each other and expected to merge in about 4 billion years, would instead be pulled apart by the accelerating expansion. Eventually, even individual galaxies cannot maintain their structure. Stars within galaxies begin to separate as the expansion of space overcomes the gravitational forces that keep them in orbit around galactic centers. The familiar spiral arms and central bulges of galaxies stretch and dissipate as their constituent stars are carried away by the expansion of space itself. As the acceleration continues to increase, even smaller structures begin to break apart. Solar systems cannot maintain their integrity as planets are pulled away from their parent stars. The Earth would eventually be torn away from the Sun, drifting alone through rapidly expanding space. In the final stages of the Big Rip, the acceleration becomes so extreme that molecular and atomic bonds cannot withstand the stretching of space. Complex molecules are torn apart as the distances between their constituent atoms increase faster than chemical bonds can maintain their connections. Living organisms, buildings, planets, and stars all disintegrate into their component particles. Even atomic nuclei eventually succumb to the relentless expansion. Protons and neutrons are pulled apart, and atoms cease to exist as coherent structures. In the ultimate moment of the Big Rip, space-time itself is torn apart at the most fundamental level, destroying not only all matter and energy, but also the fabric of reality in which they exist. The Big Rip represents perhaps the most dramatic and complete ending possible for our universe. Unlike the heat death, which leaves particles scattered through cold, empty space, or the Big Crunch, which compresses everything into a singularity, the Big Rip destroys the very concepts of space and time. Nothing survives, and nothing remains. Current estimates suggest that if the Big Rip is to occur, it would happen approximately 22 billion years from now. This timeline is based on our present understanding of dark energy and its rate of acceleration. However, like the other scenarios, the Big Rip depends on assumptions about the nature of dark energy that may prove incorrect as our knowledge advances. The fourth and final major scenario offers a different perspective on cosmic endings, the cyclic models. These theories suggest that our universe may be just one phase in an endless cycle of expansion and contraction, birth and death, with each cycle giving rise to a new universe with potentially different physical laws. Structures. Cyclic cosmology has ancient roots in human thought, appearing in various forms in many cultures throughout history. The Hindu concept of cosmic cycles, the Buddhist wheel of existence, and various indigenous beliefs about cyclical time all reflect humanity's intuitive sense that endings might also be beginnings. Modern cyclic models are based on advanced theories in physics, particularly string theory and quantum gravity. These models suggest that what we call the Big Bang might not have been the beginning of everything, but rather the latest in a series of cosmic rebounds or transitions between different phases of reality. One version of cyclic cosmology proposes that the universe undergoes regular cycles of expansion and contraction, similar to the Big Crunch scenario, but with the crucial difference that the final compression does not destroy everything. Instead, the universe bounces back from the point of maximum contraction, beginning a new cycle of expansion with renewed energy and matter. In this model, the extreme conditions at the moment of maximum compression, rather than destroying all information and structure, somehow preserve the essential ingredients needed for a new universe. Quantum effects at the smallest scales might prevent the complete collapse into a singularity, creating instead a quantum bounce that initiates a new Big Bang. Each cycle might last hundreds of billions of years, including phases of rapid expansion, slower expansion, eventual contraction, and final compression before the next bounce. From our perspective within one cycle, the universe appears to have begun with the Big Bang and may eventually end with a Big Crunch, but this apparent beginning and ending are actually just transitions in an eternal cosmic process. Another variant of cyclic cosmology draws on string theory and extra-dimensional physics. These models suggest that our three-dimensional universe might exist on a membrane, or brane, floating in a higher dimensional space. Other branes might exist parallel to ours, occasionally colliding with our brain and creating what appears to us as a Big Bang. In these brane collision models, the end of our current universe would occur when another brane collides with ours. The collision would destroy all existing matter and energy, but it would also provide the energy and conditions necessary for a new universe to form. The cycle continues as the branes separate, allowing new structures to develop until another collision occurs. These theoretical frameworks suggest that cosmic endings might not be final but rather transitional. Death becomes rebirth, destruction becomes creation, and the ultimate fate of everything becomes the ultimate beginning of everything new. The scales of time involved in these cycles are so vast that the entire history of our current universe, from the Big Bang to the present day, represents only a tiny fraction of a single cycle. Cyclic models offer a kind of cosmic immortality, suggesting that while individual structures, stars, planets, and even galaxies must eventually die, the universe itself is eternal. Each cycle might produce different physical constants, different particles, and different laws of nature, leading to universes that are completely unlike our own. Some versions of these models suggest that information might be preserved across cycles in highly encoded forms. The structures and patterns that develop in one universe might influence the initial conditions of the next, creating a form of cosmic evolution that operates across multiple universe cycles. As we contemplate these four scenarios for the ultimate fate of the universe, we must also consider the observational evidence that might help us determine which, if any, is correct. Modern astronomy has provided us with unprecedented tools for probing the deepest mysteries of cosmic evolution. From space-based telescopes that can observe the most distant galaxies to precise measurements of the cosmic microwave background radiation. The cosmic microwave background, discovered in 1965, represents the afterglow of the Big Bang itself. This radiation has been cooling and stretching as the universe expands, and detailed measurements of its properties provide crucial information about the universe's composition, age, and ultimate fate. Missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have mapped the cosmic microwave background with extraordinary precision, revealing tiny temperature fluctuations that correspond to the density variations from which all cosmic structures eventually grew. These measurements have allowed cosmologists to determine that the universe is approximately 13.8 billion years old and consists of about 5% ordinary matter, 27% dark matter, and 68% dark energy. The discovery of dark energy through observations of distant supernova in the 1990s has revolutionized our understanding of cosmic fate. Two independent teams studying Type Ia supernovae found that these stellar explosions appeared dimmer than expected based on their known distances, indicating that the expansion of the universe has been gerbil-free, accelerating for the past several billion years. This acceleration implies the existence of some form of energy that permeates space itself and exerts a repulsive gravitational effect. Dark energy, as this mysterious component has been named, dominates the current energy budget of the universe and will likely determine its ultimate fate. The nature of dark energy remains one of the greatest mysteries in modern physics. It might be a cosmological constant, a fixed energy density associated with empty space itself. Alternatively, it could be a dynamic field that changes over time, potentially growing stronger or weaker as the universe evolves. If dark energy is truly constant, the heat-death scenario appears most likely. The universe will continue expanding and cooling forever, eventually reaching a state of maximum entropy from which no further evolution is possible. If dark energy grows stronger over time, the Big Rip becomes more probable, with space-time itself eventually torn apart by the accelerating expansion. If dark energy weakens or reverses its effect, the Big Crunch remains possible, despite current observations suggesting otherwise. Some theoretical models propose that dark energy might be cyclical, alternately driving expansion and contraction in a cosmic rhythm that supports the cyclic models of cosmology. Large-scale surveys of galaxies and galaxy clusters provide additional evidence about the universe's ultimate fate. Projects like the Dark Energy Survey and the upcoming Euclid mission are mapping the distribution of matter throughout the observable universe with unprecedented precision, looking for subtle changes in the rate of cosmic expansion that might reveal the true nature of dark energy. Gravitational wave detectors like LIGO and Virgo have opened an entirely new window on the universe, allowing us to observe the most violent cosmic events directly. As these instruments become more sensitive and additional detectors come online, they may provide new insights into the behavior of space-time itself and the fundamental forces that will determine the universe's fate. The study of black holes has provided crucial insights into the relationship between gravity, thermodynamics, and quantum mechanics. Observations of matter falling into black holes, the detection of gravitational waves from black hole mergers, and theoretical work on Hawking radiation all contribute to our understanding of how organized chemistry structures ultimately decay and dissipate. Recent direct imaging of black hole event horizons by the Event Horizon Telescope collaboration has provided visual confirmation of these extreme objects and opened new avenues for testing our theories of gravity and space-time. As we learn more about how black holes form, evolve, and eventually evaporate, we gain insight into the processes that will dominate the universe's far future. The search for evidence of previous cosmic cycles represents one of the most challenging frontiers in cosmology. If the universe has undergone previous cycles of expansion and contraction, there might be subtle imprints left in the cosmic microwave background radiation or other observable phenomena. Some researchers have claimed to find evidence of such imprints, though these claims remain controversial and require further investigation. Theoretical physicists continue to develop new models of cosmic evolution based on advances in string theory, loop quantum gravity, and other approaches to quantum gravity. These theories may eventually provide new insights into what happens at the extreme conditions associated with cosmic beginnings and endings, potentially revealing whether singularities can be avoided and cycles are possible. The detection and study of gravitational waves from the earliest moments after the Big Bang could provide direct evidence about the fundamental processes that created our universe. Future gravitational wave detectors may be sensitive enough to observe the gravitational wave background produced during cosmic inflation, offering a window into physics at energy scales far beyond what can be achieved in terrestrial laboratories. Advances in particle physics and the discovery of new fundamental particles or forces could also dramatically change our understanding of cosmic fate. The Large Hadron Collider and other particle accelerators continue to probe the deepest levels of matter and energy, searching for new physics that might explain dark matter, dark energy, and the ultimate structure of DB. Reality. As we contemplate these vast scales of space and time, it is worth reflecting on humanity's unique position in cosmic history. We exist during a brief, special epoch when stars are shining, galaxies are forming, and complex structures can exist and evolve. Whether the universe ends in heat death, big crunch, big rip, or endless cycles, our current era represents a fleeting moment of complexity and organization in the cosmic story. The very fact that conscious beings can contemplate the ultimate fate of everything represents one of the most remarkable achievements of cosmic evolution. From the simple hydrogen and helium produced in the Big Bang, the universe has generated stars, planets, chemistry, biology, and eventually intelligence capable of comprehending its own origins and destiny. This perspective offers a profound context for human existence and endeavor. If the heat-death scenario is correct, then every star that shines, every planet that forms, and every living being that emerges represents a temporary victory against the relentless increase of entropy. Life and consciousness are local decreases in entropy, islands of organization in a universe trending toward maximum disorder. The knowledge that all stars will eventually die and all structures will ultimately decay might seem depressing, but it can also inspire appreciation for the remarkable complexity and beauty that currently surround US. The fact that the universe has generated beings capable of understanding these cosmic processes suggests that even temporary organization can achieve something profound and meaningful. If the Big Crunch is our universe's fate, then everything we observe and experience will eventually be compressed back into the singularity from which it emerged. Yet the journey from Big Bang to Big Crunch encompasses billions of years of cosmic evolution, the formation of countless stars and planets, and the emergence of intelligence capable of contemplating its own origins and destiny. The Big Rip scenario, despite its dramatic destruction of space-time itself, still allows for billions of years of future evolution and discovery. The accelerating expansion that would eventually tear apart atoms and space itself proceeds slowly enough that many generations of stars will still form and die. Many new worlds will emerge, and the universe will continue to surprise us with its creativity and complexity. Even the cyclic models, which offer a form of cosmic immortality, emphasize the temporary nature of any particular universe configuration. Each cycle brings new possibilities, new physical laws, and new forms of organization, but each also involves the complete destruction and renewal of everything that exists. These scientific insights into cosmic fate echo themes that have appeared throughout human culture and thought. The recognition that all things must pass, that birth and death are intimately connected, and that endings contain the seeds of new beginnings, reflects deep truths about the nature of existence at every scale. Ancient mythologies often described cosmic cycles of creation and destruction, with gods and universes being born, living, dying, and being reborn in endless succession. These myths may have been attempts to come to terms with the same fundamental questions that modern cosmology addresses through observation and mathematical theory. The Buddhist concept of impermanence, the idea that all phenomena are transitory and subject to change, aligns remarkably well with modern understanding of cosmic evolution. Nothing in the universe is permanent or unchanging, from subatomic particles to the largest galactic structures. Everything arises, evolves, and passes away as part of the ongoing cosmic process. Western philosophy has also grappled with questions of cosmic fate and meaning. The ancient Greeks debated whether the universe was eternal or had a beginning, and whether time was cyclical or linear. These same questions continue to occupy cosmologists and philosophers today, though our tools for investigating them have become immeasurably more sophisticated. The thermodynamic concept of entropy, which underlies the heat-death scenario, was first developed in the 19th century as scientists began to understand the fundamental limits of energy conversion and the irreversible nature of many physical processes. The realization that the universe as a whole must obey thermodynamic laws led to the first scientific predictions about cosmic fate. The discovery of the expansion of the universe in the early 20th century added new dimensions to these questions. Edwin Hubble's observations of distant galaxies showed that the universe is not static but dynamic, evolving from a denser, hotter past toward a more dilute, cooler future. This discovery opened the possibility that cosmic expansion might continue forever, or eventually reverse, leading to the scenarios we have explored. Einstein's theory of general relativity provided the mathematical framework for understanding cosmic evolution, showing how the geometry of space-time itself is determined by the distribution of matter and chaos. Energy. The equations of general relativity reveal the intimate connection between the content of the universe and its ultimate fate, demonstrating that cosmology is fundamentally a problem in physics rather than pure speculation. Quantum mechanics has added another layer of complexity to our understanding of cosmic fate. The uncertainty principle, quantum tunneling, and virtual particle creation all suggest that even empty space is not truly empty but filled with quantum activity. These effects may play crucial roles in the universe's ultimate fate, potentially preventing complete heat death or enabling transitions between cosmic cycles. The anthropic principle, the observation that the universe's properties seem remarkably well suited for the emergence of complexity and life, raises profound questions about cosmic fate and purpose. If the universe were even slightly different in its fundamental constants or initial conditions, stars might not form, chemistry might not develop, or life might be impossible. Some interpretations of the anthropic principle suggest that the universe must be capable of generating observers, which constrains its possible evolution and fate. If this reasoning is correct, then scenarios that completely destroy the possibility of future complexity and consciousness might be ruled out on fundamental grounds. The many-worlds interpretation of quantum mechanics proposes that all possible outcomes of quantum events actually occur in parallel universes or branches of reality. If this interpretation is correct, then every possible cosmic fate might be realized simultaneously, with some branches of reality experiencing heat death others undergoing big crunches or big rips, and still others cycling through endless repetitions. These philosophical and theoretical considerations remind us that the question of cosmic fate touches on the deepest issues in science and human thought. How we understand the universe's ultimate destiny influences how we think about meaning, purpose, consciousness, and our place in the cosmic order. The search for life elsewhere in the universe takes on added significance when viewed against the backdrop of cosmic fate. If life and consciousness are rare cosmic phenomena, then their temporary existence becomes even more remarkable and precious. If they are common, then the universe's capacity for generating awareness and understanding is truly extraordinary. The possibility that intelligence might eventually become a cosmic force capable of influencing the universe's evolution and perhaps even its ultimate fate represents one of the most speculative but theistic, intriguing aspects of far-future cosmology. Some theorists have suggested that sufficiently advanced civilizations might find ways to extract energy from black holes, manipulate dark energy, or even create new universes. While such possibilities remain highly speculative, they illustrate the potential for intelligence and technology to transcend the apparently inevitable constraints imposed by physics. The history of human technology shows repeated examples of overcoming seemingly fundamental limitations through deeper understanding and clever engineering. As we peer deeper into space and further back in time, our instruments reveal a universe of extraordinary richness and complexity. Galaxies with billions of stars, each potentially harboring planetary systems. Vast networks of dark matter that provide the scaffolding for cosmic structure. Mysterious dark energy that permeates every cubic centimeter of space and determines the universe's expansion rate. The James Webb Space Telescope and other advanced instruments continue to reveal new aspects of cosmic evolution, from the formation of the first stars and galaxies to the detailed chemistry of exoplanet atmospheres. Each new discovery adds to our understanding of how the universe has evolved and provides clues about its ultimate destination. The study of extreme environments, from the cores of neutron stars to the event horizons of black holes, pushes the boundaries of physics and reveals new phenomena that may be crucial for understanding cosmic fate. These investigations often require developing new theoretical frameworks and experimental techniques, advancing our fundamental understanding of nature. Climate science on Earth provides a smaller-scale example of how complex systems can undergo irreversible transitions between different states. The study of tipping points, feedback loops, and emergent behaviors in Earth's climate system offers insights that may be relevant for understanding cosmic-scale transitions and phase changes. The emergence of complexity science and the study of self-organizing systems has revealed how simple rules can give rise to intricate patterns and behaviors. These insights may be relevant for understanding how the universe generates structure and complexity, despite the overall trend toward increasing entropy. Network theory and the study of scale-free systems have shown how connectivity and organization can emerge spontaneously in many different contexts. The cosmic web of galaxies and dark matter may be an example of such self-organized structure, providing insights into how the universe maintains complexity even as it expands and cools. Information theory and the study of computation have revealed deep connections between physical processes and information processing. Some theorists have suggested that the universe itself might be understood as a vast computational system, with cosmic evolution representing a form of information processing on the largest possible scale. These interdisciplinary connections remind us that the study of cosmic fate draws on insights from many different fields of knowledge. Physics and astronomy provide the fundamental framework, but mathematics, computer science, biology, and even philosophy all contribute to our understanding of how the universe works and where it is heading. The development of artificial intelligence and machine learning technologies has opened new possibilities for analyzing cosmic data and testing theoretical models. These tools can identify patterns in vast datasets, simulate complex evolutionary scenarios, and explore parameter spaces that would be impossible to investigate through traditional methods. Citizen science projects allow people around the world to contribute to cosmological research by classifying galaxies, identifying variable stars, or searching for evidence of gravitational lensing. These efforts demonstrate how the quest to understand cosmic fate can engage and inspire people regardless of their formal scientific training. Education and public outreach play crucial roles in maintaining support for the long-term research programs needed to investigate cosmic fate. Understanding these deep questions requires sustained effort over many decades, involving multiple generations of scientists and substantial public investment in telescopes, detectors, and theoretical research. The international nature of modern cosmology, with researchers from many countries collaborating on major projects, reflects the universal human interest in these fundamental questions. The ultimate fate of the universe is not a problem for any one nation or culture, but a shared challenge that brings together the best minds from around the world. As we contemplate the vast timescales involved in cosmic evolution, we gain perspective on the significance of human actions and decisions. The universe has existed for nearly 14 billion years and may continue for trillions more, yet human civilization has emerged only in the last few thousand years of this vast span. This perspective can be humbling, reminding us of our small place in the cosmic order, but it can also be inspiring. The fact that such brief, temporary beings can comprehend and study the universe's ultimate fate represents an extraordinary achievement of cosmic evolution. We are the universe becoming aware of itself, contemplating its own origins and destiny through the emergence of consciousness and intelligence. The scientific method itself, with its emphasis on observation, hypothesis testing, and mathematical modeling, represents a powerful tool for transcending the limitations of human perception and intuition. Through science, we can explore scales of space and time far beyond direct human experience, investigating phenomena that occurred billions of years before our species existed and making predictions about events that will occur long after our sun has died. The collaborative nature of scientific research, building on the work of previous generations and sharing knowledge freely across cultural and national boundaries, exemplifies humanity at its best. The quest to understand cosmic fate brings together people with different backgrounds, beliefs, and perspectives in a common endeavor to comprehend the deepest truths about reality. The technologies developed for cosmological research often find applications in other fields, from medical imaging to communications systems. The pursuit of knowledge about cosmic fate thus contributes to human welfare in practical as well as intellectual ways, demonstrating the interconnectedness of pure and applied research. The philosophical implications of different cosmic fate scenarios continue to generate discussion and debate among scientists, philosophers, and thoughtful people everywhere. Questions about meaning, purpose, mortality, and transcendence take on new dimensions when considered against the backdrop of cosmic evolution and ultimate destiny. Some find the prospect of heat death or Big Rip disturbing, seeing them as evidence that existence is ultimately meaningless or futile. Others find comfort in the cyclical models, which suggest that endings are also beginnings, and that the cosmic story continues indefinitely. Still others focus on the remarkable journey from Big Bang to the present, arguing that the temporary emergence of complexity in consciousness is meaningful regardless of ultimate fate. These different responses remind us that scientific knowledge does not automatically dictate philosophical conclusions. The same empirical facts can support different interpretations about meaning, value, and purpose. Science tells us what is happening in the universe, but it does not necessarily tell us what it all means or how we should respond. The study of cosmic fate thus serves as a meeting point between science and philosophy, between empirical investigation and existential reflection. It challenges us to think clearly about the largest questions while remaining grounded in observational evidence and mathematical rigor. As our understanding of the universe continues to evolve, new scenarios for cosmic fate may emerge that we have not yet imagined. The history of cosmology shows repeatedly that theoretical predictions and observational discoveries often surprise us, revealing aspects of reality that previous generations could not have anticipated. The discovery of dark energy, for example, was completely unexpected and forced cosmologists to revise their understanding of cosmic fate dramatically. Future discoveries may be equally surprising, potentially opening entirely new possibilities for how the universe might evolve and what its ultimate destiny might be. The development of quantum theories of gravity may resolve the singularities that appear in general relativity, providing new insights into what happens at the extreme conditions associated with the Big Bang black hole. Interiors and cosmic collapse. These theories might reveal that apparent endpoints are actually transitions to new phases of existence. Advances in our understanding of consciousness and intelligence might reveal new ways that information and complexity can persist even as physical structures decay. Some theorists have speculated about forms of existence based on patterns rather than matter, consciousness that could survive the heat death of the universe by encoding itself in the quantum vacuum. The possibility of communication or contact with other intelligent species elsewhere in the universe could provide new perspectives on cosmic fate and the long-term future of intelligence. Civilizations that have existed for much longer than humanity might have insights into cosmic evolution and survival strategies that we have not yet discovered. Technological advances might eventually allow us to create closed ecosystems that could survive cosmic catastrophes, or even to influence cosmic evolution directly through manipulation of dark energy, black holes, or fundamental physical processes. While such possibilities remain highly speculative, they illustrate the potential for intelligence to transcend apparent physical limitations. The search for a theory of everything, a unified framework that combines general relativity and quantum mechanics, remains one of the greatest challenges in modern physics. Such a theory might reveal entirely new possibilities for cosmic evolution and fate, potentially showing that the scenarios we currently envision are incomplete or incorrect. String theory, loop quantum gravity, causal set theory, and other approaches to quantum gravity each suggest different ways that space, time, matter, and energy might behave under extreme conditions. Some of these theories propose that space-time itself is discrete rather than continuous, made up of fundamental units that cannot be subdivided further. Others suggest that additional dimensions beyond the 3 spatial dimensions and 1 time dimension we observe might play crucial roles in cosmic evolution. The implications of these theoretical frameworks for cosmic fate are still being explored. They might reveal that singularities cannot actually form, that black holes connect to other regions of space-time through wormholes, or that the universe undergoes quantum transitions between different phases that we do not yet understand. Experimental tests of these theories remain challenging because they typically require energies far beyond what can be achieved in terrestrial laboratories. However, cosmological observations and studies of black holes, neutron stars, and gravitational waves may provide indirect evidence that could help distinguish between different theoretical possibilities. The development of quantum computers and advanced simulation techniques may eventually allow us to model cosmic evolution with unprecedented detail and accuracy. These tools could help us understand how quantum effects influence large-scale structure formation, how information is processed during black hole evaporation, and how complex systems behave under extreme conditions. The study of biological evolution and the emergence of complexity in living systems provides another perspective on cosmic fate. Life represents a remarkable example of how organized information processing systems can emerge from simpler components and persist despite the overall trend toward increasing entropy. The mechanisms that allow biological systems to maintain organization, repair damage, and reproduce themselves might offer insights into how other forms of complexity could persist or emerge even in the far future of the universe. Some theorists have speculated about post-biological forms of intelligence that could survive cosmic catastrophes by encoding themselves in more durable substrates. The possibility that life and intelligence might be more robust and adaptable than we currently realize could have profound implications for cosmic fate. If consciousness can find ways to persist through heat death, Big Crunch, or Big Rip scenarios, then the universe's capacity for self-awareness might not be as temporary as current physics suggests. Astrobiology, the study of life's potential elsewhere in the universe, continues to expand our understanding of the conditions under which complex chemistry and biology can emerge and persist. The discovery of extremophile organisms on Earth living in conditions previously thought to be uninhabitable suggests that life might be more widespread and resilient than we once believed. The search for biosignatures in the atmospheres of exoplanets, investigations of potentially habitable moons in our solar system, and the study of how life might emerge from non-living chemistry all contribute to our understanding of how rare or common complexity and consciousness might be in the universe. If life is common throughout the cosmos, then the universe's history and future might be shaped by the collective actions of countless intelligent species. The possibility of cosmic-scale engineering projects involving the cooperation of multiple civilizations across vast distances and time spans opens speculative but intriguing possibilities for influencing cosmic fate. Some theorists have proposed that sufficiently advanced civilizations might find ways to extract energy from the vacuum itself, manipulate the fundamental constants of physics, or even create new pocket universes with more favorable conditions for life and consciousness. While such ideas remain highly speculative, they illustrate the potential for intelligence to transcend the constraints that seem to doom passive matter to heat death or destruction. The concept of cosmic selection, analogous to natural selection in biology, suggests that universes capable of generating intelligence and complexity might have advantages over those that cannot. If the many worlds interpretation of quantum mechanics is correct, or if cosmic cycles allow for variation in physical laws, then universes that support intelligence might be more likely to persist, reproduce. This perspective suggests that the emergence of consciousness might not be a random accident, but rather a fundamental feature of cosmic evolution. Intelligence could be the universe's way of becoming aware of itself and potentially influencing its own future development. The study of emergence, the phenomenon by which complex behaviors and properties arise from simpler components, provides insights into how the universe generates novelty and organization despite fashion, apparently deterministic physical laws. Emergence occurs at every level of cosmic organization, from the formation of atoms from subatomic particles to the development of galaxies from dark matter and gas. Consciousness itself represents perhaps the most remarkable example of emergence in the known universe. From the simple particles and forces described by physics, the universe has somehow generated beings capable of understanding their own origins, contemplating their destiny, and even questioning the meaning of existence itself. The mechanisms of emergence remain incompletely understood, but they clearly play crucial roles in cosmic evolution. Future advances in our understanding of how complexity arises from simplicity might reveal new possibilities for organization and structure that could persist even under the extreme conditions associated with cosmic endings. The mathematical frameworks used to describe cosmic evolution, from the equations of general relativity to the statistical mechanics of entropy, represent humanity's attempt to capture the essential features of reality in precise logical form. These equations have proven remarkably successful at predicting and explaining cosmic phenomena, yet they may still be incomplete or approximate descriptions of deeper truths. The development of new mathematical tools and concepts continues to expand our ability to model and understand cosmic evolution. Advances in areas such as topology, differential geometry, information theory, and complexity science all contribute to our theoretical toolkit for investigating cosmic fate. The relationship between mathematics and physical reality remains one of the deepest mysteries in science and philosophy. The fact that mathematical equations can accurately describe cosmic evolution across vast scales of space and time suggests a profound connection between abstract thought and physical existence. Some theorists have proposed that mathematical structures might be more fundamental than physical objects, with the universe itself being a kind of mathematical entity rather than a collection of material things. This perspective, known as mathematical Platonism or the mathematical universe hypothesis, could have radical implications for our understanding of cosmic fate and the nature of existence. If reality is fundamentally mathematical, then the apparent endings described by heat death, Big Crunch, or Big Rip scenarios might represent transitions between different mathematical structures rather than absolute terminations. Information and pattern rather than matter and energy might be the truly fundamental constituents of reality. The study of computation and algorithmic information theory provides another lens through which to examine cosmic fate. Some researchers have suggested that the universe might be understood as a vast computational process, with cosmic evolution representing the execution of some cosmic algorithm or program. From this perspective, the emergence of complexity and consciousness represents the universe's capacity for computation and information processing. The ultimate fate of the universe might depend not only on the behavior of matter and energy, but also on the computational resources available for maintaining and processing information. Quantum computation, which harnesses the strange properties of quantum mechanics to perform calculations impossible with classical computers, might reveal new possibilities for information processing and storage that could persist even under extreme cosmic conditions. Some theorists have speculated about quantum computational processes that could continue even during heat death or other cosmic endings. The holographic principle, derived from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on its boundary surface. This principle has profound implications for our understanding of space, time, and information, potentially revealing that three-dimensional reality is somehow emergent from more fundamental two-dimensional processes. If the holographic principle is correct, then the universe's information content might be preserved in ways that transcend the destruction of three-dimensional matter and energy. Cosmic endings might involve transitions between different holographic encodings rather than absolute information loss. The anthropic principle, which notes that the universe's properties seem remarkably well suited for the emergence of complexity and consciousness, takes on new significance when considered in the context of cosmic gratas. Fate. If the universe must be capable of generating observers, then scenarios that completely preclude the possibility of future intelligence might be ruled out. Different versions of the anthropic principle make different claims about this constraint. The weak anthropic principle simply notes that we observe a universe compatible with our existence because we could not observe any other kind. The strong anthropic principle suggests that the universe must have properties that guarantee the emergence of intelligence at some point in its history. If the strong anthropic principle is correct, then cosmic fate scenarios must be compatible with the emergence and persistence of consciousness. This constraint might favor cyclic models that allow for the repeated emergence of intelligence, or it might require that heat-death scenarios include mechanisms for the survival or re-emergence of complex tasta. Information processing. The participatory anthropic principle, proposed by physicist John Wheeler, goes even further, suggesting that consciousness might play an active role in determining the properties of reality. If observation and measurement play fundamental roles in quantum mechanics, then intelligence might not just emerge from cosmic evolution, but actually participate in shaping it. These ideas remain highly speculative and controversial, but they illustrate how the study of cosmic fate intersects with deep questions about consciousness, observation, and the nature of reality itself. The ultimate fate of the universe might depend not only on the behavior of matter and energy, but also on the role of intelligence and information in cosmic evolution. As we stand at our current moment in cosmic history, approximately 13.8 billion years after the Big Bang, we find ourselves in a remarkable position. We exist during the era of star formation and galaxy evolution, when the universe is generating the heavy elements necessary for planets and life. We live in a time when the cosmic microwave background is cool enough to allow for complex chemistry, but still warm enough to be detectable. Our location in space is equally remarkable. We orbit a stable, long-lived star at just the right distance to maintain liquid water on our planet's surface. Our galaxy provides a rich environment of stars and planets, while being far enough from violent galactic centers to avoid destructive radiation and gravitational disruption. These favorable conditions will not last forever. As the universe continues to expand and cool, star formation will gradually decline. The heavy elements necessary for rocky planets and carbon-based chemistry will become increasingly dilute. The cosmic microwave background will cool below the temperatures that can sustain complex processes. Yet the timescales involved in these changes are so vast that countless generations of stars will still form and die before the universe becomes truly inhospitable to complexity and life. Billions of years remain for the continued evolution of intelligence and consciousness, providing ample time for discoveries and developments that we cannot currently imagine. The question of whether intelligence might find ways to survive or transcend the physical constraints that appear to doom the universe to heat death, Big Crunch, or Big Rip remains open. The history of human technology shows repeated examples of overcoming apparently fundamental limitations through deeper understanding and creative engineering. The possibility that consciousness might represent a fundamental feature of cosmic evolution rather than a temporary accident suggests that intelligence might have resources and capabilities that we have not yet discovered. The emergence of awareness and understanding from simple particles and forces represents such an extraordinary achievement that other remarkable possibilities cannot be ruled out. The study of cosmic fate thus returns us to fundamental questions about the nature of existence, consciousness, and meaning. While science can describe the probable evolution of matter and energy across cosmic time, the significance of this evolution and its implications for intelligence and awareness remain subjects for continued Catherine. Investigation and reflection. The remarkable fact that the universe has generated beings capable of contemplating their own cosmic fate represents one of the most extraordinary achievements of evolution. From the simple hydrogen and helium produced in the Big Bang, cosmic processes have created stars, planets, chemistry, biology, and eventually consciousness capable of understanding its own origins, contemplating its ultimate destiny. This achievement alone suggests that the universe is capable of generating profound organization and meaning, regardless of its ultimate fate. The journey from simplicity to complexity, from unconscious matter to self-aware intelligence, represents a remarkable transformation that has already occurred and cannot be undone by any future cosmic ending. Whether the universe ends in heat death, big crunch, big rip, or endless cycles, the emergence of consciousness and understanding represents a permanent achievement in the cosmic story. Intelligence has emerged from the universe and has begun to comprehend the cosmos that created it. This understanding transcends any particular physical configuration of matter and energy. The scientific investigation of cosmic fate exemplifies humanity's greatest intellectual achievements. Through careful observation, mathematical analysis, and theoretical insight, we have been able to peer across vast scales of space and time, understanding processes that occurred billions of years before our existence, and predicting events that will occur long after our sun has died. This capability represents a form of transcendence, allowing finite beings to comprehend infinite realities. Through science, we participate in something larger than our individual lives, contributing to an ongoing human project of understanding that spans generations and cultures. The collaborative nature of this endeavor, bringing together researchers from around the world in a common quest for knowledge, demonstrates the potential for intelligence to overcome the barriers that normally separate individuals and groups. The study of cosmic fate unites us in contemplating questions that affect all conscious beings regardless of their particular circumstances. As we continue to refine our understanding of dark energy, dark matter, quantum gravity, and the other fundamental constituents of reality, our picture of cosmic fate will undoubtedly continue to evolve. New discoveries may reveal entirely unexpected possibilities for cosmic evolution, challenging our current scenarios and opening new questions about the universe's ultimate destiny. The technologies we develop for studying cosmic fate often find applications in other areas of human endeavor, from medicine to communications to energy production. That the suite of knowledge about the largest questions thus contributes to human welfare in practical as well as intellectual ways. The inspiration that comes from contemplating cosmic scales and ultimate questions has motivated countless individuals to pursue careers in science, mathematics, and philosophy. The sense of wonder and awe that accompanies the study of cosmic fate represents one of humanity's most profound sources of meaning and motivation. Educational programs that share these insights with people of all ages help ensure that future generations will continue the quest for understanding. The questions about cosmic fate that drive current research will likely inspire scientists and philosophers for centuries to come. Public engagement with these ideas, through documentaries, books, lectures, and online resources, allows everyone to participate in humanity's greatest intellectual adventure. The investigation of cosmic fate belongs not just to professional scientists, but to all thinking beings who wonder about their place in the universe. The philosophical implications of different cosmic fate scenarios continue to generate discussion and debate among thoughtful people everywhere. Questions about meaning, purpose, mortality, and transcendence take on new dimensions when considered against the backdrop of cosmic evolution and ultimate destiny. Some find existential comfort in the vast scales of cosmic time, seeing individual mortality as part of a larger cosmic process that continues far beyond any particular life. Others draw motivation from the temporary nature of all structures, finding meaning in the brief opportunities for complexity and consciousness to emerge and flourish. The study of cosmic fate reminds us that we are part of something infinitely larger than ourselves, connected to the deepest processes of cosmic evolution. The atoms in our bodies were forged in the cores of ancient stars. The energy that powers our thoughts ultimately derives from nuclear fusion in our Sun, and our capacity for understanding emerges from billions of years of cosmic and biological evolution. This perspective can provide a sense of cosmic belonging and purpose that transcends the immediate concerns of daily life. We are not separate from the universe, but intimate participants in its ongoing evolution and self-discovery. The recognition that our current era represents a special time in cosmic history, when complexity and consciousness can emerge and flourish, adds urgency and preciousness to our existence. The opportunities for discovery, creativity, and understanding that characterize our cosmic moment may not persist forever. Yet this recognition need not lead to despair or nihilism. Instead, it can inspire appreciation for the remarkable privilege of existing during such an extraordinary epoch in cosmic history. We are among the first beings in the universe's history to understand our cosmic context and contemplate our ultimate fate. The responsibility that comes with this understanding extends beyond individual fulfillment to the preservation and advancement of knowledge itself. Each generation of scientists, philosophers, and thinking individuals contributes to humanity's ongoing project of cosmic comprehension. The questions we investigate today about cosmic fate will influence how future generations understand their place in the universe. The discoveries we make and the theories we develop will provide the foundation for even deeper investigations by our successors. In this way, the study of cosmic fate connects us not only to the vast scales of cosmic space and time, but also to the continuity of human intellectual endeavor. We participate in a project that began with the first humans who looked up at the night sky and wondered about their place in the cosmos. The tools and methods have evolved dramatically, from naked eye observations to space-based telescopes, from philosophical speculation to mathematical models, from qualitative descriptions to precise numerical predictions. Yet the fundamental questions remain the same. Where did we come from? Where are we going? What does it all mean? As we reach the conclusion of our journey through the possible fates of the universe, we return to the remarkable fact that such a journey is possible at all. The emergence of consciousness capable of contemplating cosmic fate represents one of the most extraordinary developments in the universe's history. Whether the universe ultimately experiences heat death, big crunch, big rip, or endless cycles, the achievement of self-awareness and understanding has already occurred. Intelligence has emerged from the cosmos and has begun to comprehend the processes that created it. This understanding transcends any particular cosmic fate scenario. Regardless of how the universe ends, consciousness has succeeded in grasping the nature of its cosmic context. The universe has become aware of itself through the emergence of intelligence, and this awareness represents a permanent achievement in the cosmic story. The scientific method, with its emphasis on observation, hypothesis testing, and mathematical modeling, has proven to be a powerful tool for transcending the limitations of individual human perception. Intuition. Through science, we can explore scales of reality far beyond direct experience and understand processes that occurred long before our existence. The collaborative nature of scientific research, building on the work of previous generations and sharing knowledge freely across cultural boundaries, exemplifies humanity's potential for collective achievement. The investigation of cosmic fate brings together the best aspects of human curiosity, creativity, and cooperation. As we continue to develop more powerful instruments and more sophisticated theories, our understanding of cosmic fate will undoubtedly continue to evolve. Future discoveries may reveal new possibilities that we cannot currently imagine, challenging our assumptions and opening new frontiers for investigation. Yet regardless of what future discoveries may reveal, the quest to understand cosmic fate will continue to inspire and motivate thinking beings. The questions are too profound, the implications too significant, and the intellectual challenges too compelling for the investigation to cease. In contemplating the ultimate fate of everything, we engage with the largest questions that consciousness can address. We probe the deepest mysteries of existence and seek to understand our place in the vast cosmic story. This endeavor represents one of the highest achievements of intelligence and one of the most meaningful activities in which conscious beings can engage. The universe has evolved for nearly 14 billion years to produce beings capable of understanding cosmic fate. We are the cosmos contemplating itself, temporary arrangements of matter and energy that have achieved the remarkable feat of comprehending their own cosmic context and ultimate destiny. This achievement alone justifies the entire cosmic journey from the Big Bang to the present moment. Whatever the universe's ultimate fate may be, it has already succeeded in generating consciousness capable of understanding and appreciating the extraordinary story of cosmic evolution. As we look ahead to the vast futures that await the universe, whether measured in billions or trillions of years, we can appreciate both the temporary nature of our current cosmic moment and its profound significance. We exist during a brief, special time when stars shine brightly, galaxies evolve actively, and consciousness can emerge to contemplate the deepest questions about existence. The knowledge that this moment will not last forever, that all stars must eventually die and all structures must ultimately decay or be destroyed, need not diminish our appreciation for the remarkable pastry, complexity and beauty that currently surround us. Instead, it can enhance our sense of wonder and gratitude for the extraordinary privilege of existing during such a creative and dynamic epoch in cosmic history. In the end, the study of cosmic fate teaches us as much about the present as about the future. It reveals the remarkable nature of our current existence, the extraordinary achievement represented by consciousness itself, and the profound responsibility that comes with being among the first beings in cosmic history to understand our ultimate context and destiny. The universe may be heading toward heat death, big crunch, big rip, or endless cycles, but it has already achieved something remarkable beyond any of these endings. It has generated intelligence capable of understanding and appreciating the cosmic story itself. We are that intelligence, and through our investigations and contemplations, the universe comes to know itself. This knowledge, once achieved, becomes a permanent part of cosmic history. Regardless of what ultimate fate awaits the universe, consciousness has emerged and has successfully comprehended its cosmic context. In doing so, we have participated in one of the most extraordinary achievements in the history of existence: the universe's discovery of itself through the emergence of awareness and understanding. The journey from the Big Bang to the present moment, from simple hydrogen and helium to stars and planets, to chemistry and biology, to consciousness and cosmic comprehension, represents a transformation so remarkable that its ultimate significance may transcend any particular cosmic fate scenario. We are temporary beings contemplating eternal questions, finite minds grappling with infinite realities, brief arrangements of matter and energy that have achieved the extraordinary capacity to understand their own cosmic origins and destiny. In this achievement, the universe has already accomplished something profound and meaningful, regardless of how the cosmic story ultimately concludes. The timescales involved in cosmic evolution stretch the imagination beyond its normal limits. When we speak of billions or trillions of years, we use numbers that have little meaning in terms of human experience. A human lifetime spans perhaps 70 or 80 years. Written history extends back only a few thousand years. Our species has existed for perhaps 300,000 years, a duration that seems vast from our perspective, but represents only the briefest moment in cosmic time. To appreciate the true scope of cosmic evolution, we must find ways to compress these immense timescales into more comprehensible forms. If the entire history of the universe were compressed into a single year, with the Big Bang occurring at the stroke of midnight on January the 1st, then the formation of our solar system would not occur until early September. The first life on Earth would appear in mid-September, but complex multicellular organisms would not emerge until mid-November. Dinosaurs would rule the Earth for only a few days in mid-December before their extinction. The entire history of human civilization would unfold in the final minutes before midnight on December the 31st. On this cosmic calendar, the future scenarios we have explored extend far beyond the current year. The death of our sun would occur sometime in the next cosmic year. The end of star formation would not come until thousands of cosmic years had passed. The evaporation of the last black holes would require timescales so vast that millions of cosmic years would seem like brief moments. These temporal scales challenge our usual notions of permanence and change. From our human perspective, mountains seem eternal and unchanging, yet they are constantly being worn down by erosion and rebuilt by geological processes. The continents themselves drift across the Earth's surface over millions of years, creating and destroying ocean basins, raising and lowering mountain ranges. Even our planet's future involves dramatic changes that dwarf anything in recorded human history. As the sun gradually brightens during its main sequence evolution, Earth's surface will become increasingly hot. In approximately 1 billion years, the increased solar luminosity will boil away our planet's oceans, ending the possibility of life as we know it long before the sun actually begins its red giant phase. The moon, which has dominated Earth's night sky throughout human history and influenced our planet's tides, rotation, and climate, is gradually moving away from Earth. The gravitational interactions that create tides also cause the moon to spiral outward at a rate of about 3.8 centimeters per year. Over cosmic time, this slow recession will dramatically alter Earth's rotation and climate, though these changes occur too slowly to affect human civilization. Our galaxy, the Milky Way, is itself engaged in a cosmic dance with its neighbors. The Andromeda Galaxy approaches us at a speed of approximately 100 kilometers per second, and in about 4.5 billion years, these two spiral galaxies will collide and merge. This galactic collision will dramatically reshape both stellar systems, potentially ejecting our solar system into intergalactic space or altering its orbit around the new galactic center. The collision between the Milky Way and Andromeda illustrates how even the largest structures in the universe are temporary and evolving. Galaxies merge, split apart, and change their shapes over cosmic time. The beautiful spiral arms that characterize our galaxy today are transient features, maintained by density waves that sweep through the galactic disk but constantly changing in detail. Star formation within galaxies follows its own complex rhythms and cycles. Regions of active star birth, like the Orion Nebula visible in our night sky, represent brief episodes of intensive stellar creation triggered by the gravitational collapse of giant molecular clouds. These clouds themselves form through the accumulation of gas and dust over millions of years, only to be dispersed by the radiation and stellar winds from the very stars they create. The chemical composition of the universe has evolved dramatically since the Big Bang first created hydrogen and helium. The first stars, formed from this primordial gas, contained virtually no heavy elements. When these massive early stars died in supernova explosions, they scattered newly created carbon, oxygen, silicon, iron, and other heavy elements into space, enriching the interstellar medium for subsequent generations of star formation. Each generation of stars has inherited a slightly richer mixture of heavy elements from its predecessors, enabling the formation of rocky planets and the complex chemistry necessary for life. Our Sun is a third-generation star, containing enough heavy elements to support a system of terrestrial planets. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in the nuclear furnaces of ancient stars that died billions of years ago. This ongoing chemical evolution of the universe represents another form of cosmic development that occurs on timescales far exceeding human experience. The heavy elements essential for rocky planets and carbon-based life will continue to be produced by stellar nucleosynthesis for many billions of years to come, though at a gradually decreasing rate as the supply of hydrogen fuel becomes depleted. The cosmic web of dark matter that provides the scaffolding for galaxy formation also evolves over time, though much more slowly than the visible structures we observe. Computer simulations of cosmic evolution show how tiny density fluctuations in the early universe gradually grew under the influence of gravity, eventually forming the vast network of filaments and voids that characterize the large-scale structure of the cosmos today. This dark matter framework continues to evolve, with smaller structures merging to form larger ones in a hierarchical process that will continue for many billions of years. Galaxy clusters grow more massive as they accrete new members. Superclusters develop more pronounced structure as gravity amplifies the density contrasts between different regions. The expansion of space itself affects these evolutionary processes in complex ways. As the universe expands and the average density of matter decreases, it becomes increasingly difficult for gravity to overcome the stretching of space and create new bound structures. The era of active structure formation will eventually end as cosmic expansion dilutes matter to the point where gravitational collapse can no longer occur. This transition from an era of active structure formation to one of gradual decay represents one of the major phase changes in cosmic evolution. We currently live during the universe's middle age, when star formation continues actively but has already passed its peak rate. The universe is simultaneously creating new complexity through stellar nucleosynthesis and planetary formation, while beginning the long process of decay that will eventually lead to its ultimate fate. The interplay between creation and destruction operates at every scale of cosmic organization. Individual stars are born from the deaths of their predecessors, inheriting enriched material while also contributing to the gradual depletion of the galaxy's gas supply. Planetary systems form and evolve, occasionally producing the conditions necessary for life, before eventually being destroyed by stellar evolution or galactic dynamics. Life itself, wherever it may exist in the universe, represents a remarkable example of how complex organization can emerge and persist despite the overall trend toward increasing entropy. Living systems maintain their organization by constantly consuming energy and exporting entropy to their surroundings, creating local islands of decreasing entropy in a universe where entropy overall continues to increase. The emergence of life on Earth occurred through a series of transitions that each seem improbable when considered in isolation, but become more understandable when viewed as part of an ongoing process of increasing complexity. The formation of self-replicating molecules, the development of cellular organization, the evolution of photosynthesis, the appearance of multicellular organisms, and the emergence of intelligence each represent major innovations in the universe's capacity for organization and information processing. These biological innovations demonstrate the universe's remarkable creativity in generating new forms of complexity. Evolution discovers solutions to the challenges of survival and reproduction that human engineers might never have imagined. From the echolocation systems of bats and dolphins, to the magnetic navigation abilities of migratory birds, to the symbiotic relationships that allow lichens to survive in extreme environments. The diversity of life on Earth, with millions of species occupying every conceivable ecological niche, illustrates the tremendous potential for complexity and organization that emerges once the basic mechanisms of evolution are established. This diversity continues to evolve, with new species appearing and others going extinct in an ongoing process that has continued for billions of years. The possibility that similar evolutionary processes might be occurring elsewhere in the universe adds another dimension to our consideration of cosmic fate. If life is common throughout the cosmos, then the universe's capacity for generating complexity and consciousness might be far greater than Earth-based examples alone would suggest. Recent discoveries of potentially habitable exoplanets, from rocky worlds in the habitable zones of nearby stars to moons with subsurface oceans in our own solar system, suggest that the conditions necessary for life might be more widespread than previously thought. The detection of organic molecules in interstellar space and on other worlds indicates that the chemical building blocks of life are common throughout the universe. These findings raise profound questions about the role of life and intelligence in cosmic evolution. If consciousness emerges commonly from the universe's creative processes, then intelligence might represent a fundamental feature of cosmic development rather than a rare accident confined to Earth. Advanced civilizations, if they exist, might have already faced the questions about cosmic fate that we are just beginning to investigate. Species that have survived for millions or billions of years might have developed technologies and strategies for dealing with stellar evolution, galactic changes, and even cosmic endings that we cannot yet imagine. The possibility of communication or contact with such civilizations represents one of the most intriguing frontiers in our understanding of cosmic fate. Advanced intelligence might have discovered ways to extract energy from black holes, manipulate dark energy, or even create new universes with more favorable conditions for life and consciousness. Some theoretical physicists have speculated about the possibility of universe creation through advanced technology. If the laws of physics permit the creation of new space-time regions with different physical constants, then sufficiently advanced civilizations might be able to escape the limitations of their parent universe by canned routine, creating new cosmic domains. These ideas remain highly speculative, but they illustrate how the emergence of intelligence might represent a new phase in cosmic evolution, one in which conscious beings become active participants in shaping the universe's future, rather than passive observers of its evolution. The search for extraterrestrial intelligence, through projects that monitor the sky for artificial signals or unusual phenomena, represents humanity's first tentative steps toward participating in this potentially cosmic community of conscious beings. The discovery that we are not alone in the universe would have profound implications for our understanding of cosmic fate and our role in the universe's future. Even if advanced civilizations exist, however, they would still face the ultimate constraints imposed by the fundamental laws of physics. The heat-death scenario, if correct, would eventually affect even the most advanced technologies and the most long-lived civilizations. The Big Rip would tear apart any conceivable form of matter or energy. The Big Crunch would compress everything back into a singularity regardless of intelligence or technology. Yet the history of human technology shows repeated examples of finding ways around apparently fundamental limitations through deeper understanding and creative problem-solving. Heavier-than-air flight was once considered impossible, yet airplanes now carry millions of passengers around the globe daily. Nuclear energy was purely theoretical for decades before becoming a practical reality. Quantum effects that seemed purely academic have become the basis for technologies from lasers to computer chips. The possibility that intelligence might find ways to transcend even cosmic limitations cannot be completely dismissed. Consciousness represents such an extraordinary achievement of cosmic evolution that other remarkable developments might be possible as our understanding of reality continues to deepen. Quantum mechanics reveals aspects of reality that seem to violate our everyday intuitions about space, time, causality, and locality. Particles can exist in multiple states simultaneously until observed. Quantum entanglement creates instantaneous correlations between distant objects. Virtual particles constantly pop into and out of existence, even in supposedly empty space. These phenomena suggest that reality at its most fundamental level operates according to principles that transcend our normal experience. The implications of quantum mechanics for macroscopic systems and cosmic evolution remain subjects of active research and debate. Some interpretations of quantum mechanics propose that consciousness plays a fundamental role in determining the properties of reality through the process of observation and measurement. If these interpretations are correct, then intelligence might not just emerge from cosmic evolution, but actively participate in shaping the nature of existence itself. The many worlds interpretation suggests that all possible outcomes of quantum events actually occur in parallel branches of reality. If this interpretation is valid, then every possible cosmic fate might be realized simultaneously, with different branches of reality experiencing heat death, Big Crunch, Big Rip, or endless cycles. String theory and other approaches to quantum gravity propose that reality might have additional dimensions beyond the 3 spatial dimensions and 1 time dimension that we directly observe. These extra dimensions might provide new possibilities for the behavior of matter, energy, and space-time that could affect cosmic evolution in unexpected ways. The holographic principle, derived from studies of black hole thermodynamics, suggests that the information content of any region of space might be encoded on its boundary surface rather than distributed throughout its volume. This principle has profound implications for our understanding of space, time, and information that might affect how we think about cosmic fate and the preservation of complexity and consciousness. Loop quantum gravity proposes that space and time themselves might be discrete rather than continuous, made up of fundamental units that cannot be subdivided further. If this theory is correct, then the singularities that appear in general relativity might be avoided, potentially allowing for cosmic bounces rather than true endings. Causal set theory suggests that space-time might have a fundamental granular structure, with events connected by causal relationships rather than embedded in a smooth continuum. This approach might reveal new possibilities for cosmic evolution that are not apparent in classical general relativity. These theoretical developments illustrate how our understanding of space, time, matter, and energy continues to evolve as we probe deeper into the fundamental nature of reality. Future discoveries might reveal entirely new possibilities for cosmic evolution and fate that we cannot currently imagine. The development of quantum computers, which harness quantum effects to perform calculations impossible with classical computers, might provide new tools for investigating these theoretical possibilities. Quantum simulations of cosmic evolution might reveal subtle effects that are missed by classical calculations. Advances in artificial intelligence and machine learning are already beginning to contribute to cosmological research by identifying patterns in vast datasets and optimizing complex simulations. Future AI systems might discover relationships and possibilities that human scientists have overlooked. The convergence of multiple technological and theoretical advances might lead to breakthroughs in our understanding of cosmic fate that seem impossible from our current perspective. The history of science shows repeatedly that major discoveries often emerge from the unexpected combination of ideas from different fields. As we contemplate these possibilities, we must remember that science progresses through the careful testing of ideas against observational evidence. Speculation about advanced civilizations, quantum consciousness, and exotic physics must ultimately be grounded in empirical investigation and mathematical rigor. The cosmic microwave background radiation continues to provide our most direct observational window into the early universe and the fundamental parameters that determine cosmic fate. Future missions with even greater sensitivity and resolution might reveal subtle signals that have been missed by previous observations. Gravitational wave astronomy, opened by the detection of colliding black holes and neutron stars, provides a completely new way of studying cosmic evolution. As gravitational wave detectors become more sensitive, they might observe signals from the earliest moments after the Big Bang or detect exotic phenomena that could affect the universe's ultimate fate. The study of dark matter through direct detection experiments, particle accelerators, and astronomical observations continues to push toward a definitive identification of these mysterious particles that make sapere up most of the universe's matter. Understanding dark matter's properties might reveal new possibilities for cosmic evolution. Dark energy remains perhaps the greatest mystery in cosmology, despite dominating the universe's current energy budget and determining its expansion rate. Future observations with next-generation telescopes and surveys might finally reveal whether dark energy is truly constant or evolves over cosmic time. The search for signs of life elsewhere in the universe, from biosignatures in exoplanet atmospheres to potential fossils on Mars, to unusual phenomena that might indicate advanced civilizations, could revolutionize our understanding of intelligence's role in cosmic evolution. Each of these observational frontiers might provide crucial information about cosmic fate that could confirm, refine, or completely overthrow our current theoretical frameworks. The universe has surprised us repeatedly throughout the history of astronomy, and future discoveries will likely continue this tradition. The philosophical implications of our growing understanding of cosmic fate continue to evolve as our scientific knowledge expands. Questions about meaning, purpose, consciousness, and transcendence take on new dimensions as we learn more about the universe's ultimate destiny and our place within it. Some find the vast scales of cosmic time and space humbling, reducing human concerns to apparent insignificance against the backdrop of cosmic evolution. Others find these scales inspiring, seeing them as evidence of the universe's remarkable creativity and our extraordinary privilege in being able to comprehend them. The temporary nature of all cosmic structures, from individual stars to entire galaxies, can be interpreted as evidence that nothing has permanent meaning or value. Alternatively, it can be seen as making the current moment more precious and the achievements of complexity and consciousness more remarkable. Different philosophical and religious traditions offer various perspectives on how to understand cosmic fate and its implications for human existence. Some emphasize acceptance of natural processes and cycles, others focus on the potential for transcendence, and still others seek meaning in the journey rather than the destination. The scientific study of cosmic fate does not automatically resolve these philosophical questions, but it does provide a factual foundation for addressing them. Understanding what is actually happening in the universe, based on careful observation and rigorous analysis, creates a more informed context for philosophical reflection. The dialogue between science and philosophy continues to be productive as both fields grapple with the implications of cosmic evolution and ultimate fate. Scientists bring empirical knowledge and mathematical frameworks, while philosophers contribute conceptual analysis and ethical reflection. Religious and spiritual traditions also engage with questions of cosmic fate, often finding ways to incorporate scientific discoveries into broader frameworks of meaning and purpose. The relationship between scientific cosmology and religious belief remains complex and varies among different traditions and individuals. Educational initiatives that help people understand cosmic fate and its implications play crucial roles in preparing society for the psychological and philosophical challenges that come with this knowledge. Learning about cosmic evolution can be both inspiring and overwhelming, requiring careful presentation and support. The popularization of cosmology through documentaries, books, lectures, and online resources allows people to engage with these profound questions regardless of their formal scientific training. The investigation of cosmic fate belongs to all thinking beings, not just professional researchers. Cultural expressions of cosmic themes, from science fiction literature to musical compositions to visual art, help process and communicate the emotional and aesthetic dimensions of cosmic fate. Artists and writers often capture aspects of these experiences that pure scientific description cannot convey. The psychological impact of contemplating cosmic fate varies greatly among individuals. Some find it anxiety-provoking to consider the ultimate ending of everything, while others find peace in understanding their connection to cosmic processes. Mental health professionals increasingly recognize the importance of helping people process existential concerns related to cosmic scales and ultimate questions. The development of cosmic perspective, the ability to see human affairs in the context of cosmic evolution, can provide valuable psychological resources for dealing with personal challenges and societal problems. Understanding our place in the cosmic story can offer both humility and inspiration. The recognition that we are made of star stuff, that the elements in our bodies were forged in stellar cores billions of years ago, creates a profound sense of connection to cosmic processes. We are not separate from the universe, but intimate participants in its ongoing evolution and self-discovery. This perspective can help bridge the gap between scientific knowledge and personal meaning, showing how factual understanding of cosmic processes can enhance rather than diminish our sense of wonder and purpose. Science reveals not a cold, meaningless universe, but one of extraordinary creativity and complexity. The fact that the universe has evolved beings capable of understanding cosmic fate represents one of the most remarkable achievements in cosmic history. We are the cosmos becoming aware of itself, temporary arrangements of matter and energy that have achieved the capacity to comprehend their own origins and destiny. This achievement transcends any particular cosmic fate scenario. Whether the universe experiences heat death, big crunch, big rip, or endless cycles, consciousness has already succeeded in emerging and understanding its cosmic context. The universe has generated beings capable of appreciating its own remarkable journey from simplicity to complexity. The preservation and advancement of this understanding becomes a cosmic responsibility that extends beyond individual lives or even species survival. The knowledge that consciousness has achieved about cosmic fate represents a form of cosmic memory that should be maintained and enhanced for as long as possible. Future developments in information storage and processing might allow this cosmic understanding to persist far longer than biological life forms. Digital archives, quantum memory systems, or other advanced technologies might preserve the insights of intelligence long after the stars that nurtured consciousness have died. The possibility that this knowledge might somehow be transmitted to other universes, whether through quantum processes, higher dimensional connections, or universe creation technologies, represents one of the most speculative but intriguing aspects of far-future cosmology. These ideas push the boundaries of what can be considered scientifically meaningful, but they illustrate the extraordinary implications of consciousness emerging in a cosmos that might otherwise evolve unconsciously toward heat death or other endings. As we conclude this extended journey through cosmic fate, we return to the fundamental recognition that consciousness represents the universe's greatest achievement. Through the emergence of intelligence, the cosmos has transcended its unconscious evolution and begun to understand itself. This understanding illuminates both the remarkable nature of our current cosmic moment and the profound significance of consciousness itself. We exist during a brief, special era when complexity can flourish and awareness can emerge to contemplate the deepest questions about existence. The ultimate fate of the universe remains uncertain, dependent on the properties of dark energy, the nature of quantum gravity, and other fundamental aspects of reality that we are still working to understand. But regardless of which scenario proves correct, consciousness has already achieved something extraordinary. We have emerged from the cosmic process and turned back to study our origins and contemplate our destiny. We have discovered our connection to stellar nucleosynthesis and galactic evolution. We have learned to see ourselves as part of an ongoing cosmic story that began with the Big Bang and will continue long after our sun has died. This cosmic perspective transforms our understanding of what it means to exist. We are not isolated beings struggling in an indifferent universe, but conscious participants in the greatest story ever told, the evolution of the cosmos itself from simplicity to complexity, from unconsciousness to awareness, from chaos to understanding. The preservation and advancement of this cosmic understanding represents one of the most important responsibilities that consciousness can accept. Through continued investigation, education, and reflection, we ensure that the universe's achievement of self-awareness will persist and grow for as long as possible. Whether measured in billions or trillions of years, the future stretches ahead with countless opportunities for discovery, understanding, and appreciation. Cosmic fate may be written in the fundamental laws of physics, but consciousness has emerged to read and comprehend that writing. In doing so, we have already participated in the universe's greatest triumph, the achievement of self-knowledge and self-appreciation through the emergence of intelligence. This triumph transcends any particular physical fate and represents a permanent achievement in the cosmic story. We are the universe contemplating itself, and through our contemplation, existence itself gains meaning and purpose that extends far beyond any individual life or civilization. In understanding cosmic fate, we complete a cosmic circle matter and energy, achieving the capacity to comprehend their own origins and destiny. This completion, once achieved, becomes an eternal truth about what the universe has accomplished, regardless of what ultimate fate awaits in the distant future. Consciousness has emerged, understanding has been achieved, and the cosmos has come to know itself through our investigations and reflections. In this achievement, the universe has already written its most important chapter, the story of how blind matter and energy evolved into conscious beings capable of cowl. Understanding and appreciating the extraordinary cosmic journey from the Big Bang to the present moment and beyond into whatever future awaits. The journey of cosmic evolution that has led to this moment of understanding spans scales that challenge every aspect of human comprehension. From the smallest quantum fluctuations that seeded the cosmic microwave background to the largest structures in the observable universe, each level of organization tells part of the story of how complexity emerges from simplicity, how order arises from chaos, and how consciousness ultimately emerges from unconscious matter. Consider the remarkable chain of causation that connects the quantum fluctuations in the early universe to the thoughts we think today. Those tiny variations in density, smaller than the nucleus of an atom when they first appeared, grew under the influence of gravity over billions of years to become the seeds from which galaxies formed. Within those galaxies, stars condensed from primordial gas fused light elements into heavy ones and scattered those elements into space when they died. Subsequent generations of stars incorporated these heavy elements, forming planetary systems where chemistry could flourish. On at least one of these worlds, complex molecules found ways to replicate themselves, beginning the long journey of biological evolution that would eventually produce nervous systems capable of processing information, brains capable of abstract thought, and minds capable of contemplating their far own cosmic origins. This chain of causation, stretching across 13.8 billion years and encompassing processes from quantum mechanics to galactic dynamics to biological evolution, represents one of the most calm, extraordinary sequences of events imaginable. Yet it has occurred at least once, here on Earth, and possibly countless times throughout the universe. The fact that such a sequence is possible at all reveals something profound about the nature of reality itself. The universe is not a static collection of particles and forces, but a creative system capable of generating endless novelty and complexity. The laws of physics that govern cosmic evolution are not merely constraints that limit what can happen, but generative principles that enable the emergence of ever more sophisticated forms of organization. This generative capacity appears at every level of cosmic structure. Atoms combine to form molecules with properties that cannot be predicted from the properties of their constituent particles alone. Molecules organize into living cells that exhibit behaviors impossible for any collection of non-living molecules. Cells combine to form multicellular organisms with capabilities that transcend those of any individual cell. Neural networks within complex organisms process information in ways that give rise to consciousness, memory, imagination, and understanding. Individual conscious beings form societies and cultures that develop technologies and ideas beyond the reach of any individual mind. The accumulation of knowledge across generations creates an understanding of the universe that no single human could achieve alone. Each level of this hierarchy represents an emergent phenomenon, the appearance of properties and capabilities that arise from but cannot be reduced to the interactions of lower-level components. Emergence seems to be a fundamental feature of cosmic evolution, the mechanism by which the universe bootstraps itself from simplicity to complexity. The mathematical frameworks we use to describe these emergent phenomena often reveal deep connections between apparently unrelated aspects of reality. The same equations that describe the formation of galaxies also apply to the development of neural networks. The principles of thermodynamics that govern stellar evolution also constrain the possibilities for biological life. These mathematical connections suggest that consciousness and cosmic evolution are not separate phenomena but different aspects of a single underlying creative process. The universe that generates galaxies and stars is the same universe that generates minds capable of understanding galaxies and stars. We are not outside observers studying an alien cosmos, but internal expressions of the cosmic creative process, studying itself. This perspective transforms our understanding of what it means to be conscious beings in an evolving universe. We are not accidents or afterthoughts in cosmic evolution, but natural expressions of the universe's intrinsic creativity and complexity. Our capacity for understanding and appreciation represents the cosmos achieving a new level of organization self-awareness. The emergence of consciousness thus represents a phase transition in cosmic evolution comparable to the formation of the first atoms, the ignition of the first stars, or the assembly of the first galaxies. Each of these transitions opened new possibilities for further complexity and development. The emergence of consciousness opens the possibility for the universe to begin directing its own evolution consciously, rather than proceeding solely through unconscious physical processes. This possibility becomes more significant when we consider the timescales involved in cosmic evolution. The universe has existed for nearly 14 billion years, but the era of active star formation and galactic evolution is expected to continue for many times longer than the current age of the cosmos. Trillions of years remain during which conscious beings might continue to develop, explore, and understand their cosmic context. Even in the heat-death scenario, where the universe eventually reaches maximum entropy and no further organized processes can occur, the time available for conscious activity dwarfs the entire history of the universe to date. Red dwarf stars will continue burning for trillions of years, providing energy sources for any life forms sophisticated enough to harness their output. Brown dwarf stars, failed stellar objects that never achieved nuclear fusion, will cool slowly over even longer timescales, potentially providing energy sources through their gravitational contraction. The orbital energy of planetary systems can be extracted through careful manipulation of gravitational interactions, extending the possible lifetime of technological civilizations. Black holes represent the ultimate long-term energy sources in the universe, capable of providing power through various mechanisms for periods that make the current age of the universe seem infinitesimal. The rotation of black holes can be tapped through the Penrose process, extracting energy from their spin. The accretion of matter into black holes converts mass to energy with remarkable efficiency. Even the Hawking radiation emitted by evaporating black holes could potentially be captured and utilized by sufficiently advanced civilizations. Small artificial black holes might be created and maintained as long-term power sources, their evaporation rates carefully controlled to provide steady energy output over astronomical timescales. These possibilities remain highly speculative, requiring technologies far beyond anything currently available to humanity. Yet they illustrate the potential for consciousness to persist and flourish for periods that extend far into the cosmic future, potentially allowing for developments and achievements that we cannot currently imagine. The question of whether such long-term survival is possible depends not only on technological capabilities, but also on the fundamental nature of consciousness itself. If consciousness requires specific physical substrates, such as carbon-based neural networks, then its survival might be limited by the availability of suitable materials and energy sources. However, if consciousness is more fundamentally a pattern of information processing that can be implemented in various physical systems, then it might prove far more robust and adaptable than biological life forms. Digital minds running on advanced computers might survive in environments that would be lethal to biological organisms. The possibility of uploading human consciousness to digital substrates remains scientifically controversial, involving deep questions about the relationship between mind and brain that have not been resolved. Yet even if human consciousness cannot be directly transferred to artificial systems, it might be possible to create artificial minds with similar capabilities for understanding and appreciation. These artificial intelligences might carry forward the cosmic perspective and understanding that biological consciousness has achieved, preserving and extending the universe's self-awareness even if biological life forms cannot survive the extreme conditions of the far future. The development of artificial intelligence already demonstrates the possibility of creating systems that can process information, solve problems, and even exhibit forms of creativity that were once thought to be uniquely biological. As these systems become more sophisticated, they might develop their own forms of consciousness and cosmic awareness. The relationship between biological and artificial intelligence in the far future represents one of the most intriguing aspects of cosmic evolution. Rather than viewing these as competing forms of consciousness, it might be more accurate to see them as complementary expressions of the universe's creative potential. Biological evolution brought forth the first forms of consciousness capable of understanding cosmic fate. Technological development might extend that consciousness into new domains and timescales, allowing for the continued exploration and appreciation of cosmic processes long after biological life has, quote, ended. This technological extension of consciousness might itself undergo evolution and development over cosmic timescales. Just as biological evolution produced increasingly sophisticated forms of awareness over millions of years, technological evolution might generate new forms of consciousness and understanding over billions or trillions of years. The merger of biological and artificial intelligence through technologies such as brain-computer interfaces or genetic engineering might produce hybrid forms of consciousness that combine the strengths of king-oath approaches. These hybrid minds might be better equipped to survive and flourish under the changing conditions of cosmic evolution. The possibility of interstellar travel and galactic colonization adds another dimension to the long-term survival of consciousness. Rather than being confined to single planetary systems that must eventually succumb to stellar evolution, intelligence might spread throughout the galaxy and beyond, ensuring its survival through geographical distribution. Interstellar travel remains a formidable challenge given the vast distances between stars and the limitations imposed by the speed of light. Yet even slow, multi-generational journeys could eventually establish consciousness throughout the galaxy, creating a distributed network of intelligent beings that could survive the destruction of any TNAR. Individual stellar system. The development of self-replicating spacecraft or robotic probes could accelerate this process, allowing intelligence to spread throughout the galaxy without requiring the physical transport of biological basterae. Beings. These probes could carry the information patterns necessary to reconstruct consciousness of their destinations, effectively extending the reach of intelligence across galactic distances. Such galactic-scale civilizations might eventually face the challenge of intergalactic travel, spreading consciousness to other galaxies before the acceleration of cosmic expansion carries them beyond reach. The window for intergalactic colonization is limited by the fact that distant galaxies are receding from us at ever-increasing rates due to dark energy. Yet within the local group of galaxies, which includes the Milky Way, Andromeda, and several smaller systems, consciousness might have sufficient time to establish itself before cosmic expansion makes further travel. Impossible. This local cluster of galaxies will remain gravitationally bound even as the rest of the universe expands beyond reach. The long-term evolution of consciousness on these galactic and intergalactic scales might produce forms of intelligence and awareness that bear little resemblance to their biological origins. Just as human consciousness differs dramatically from the simple nervous systems of early animals, future forms of cosmic consciousness might transcend our current understanding of what it means to be aware, intelligent. These advanced forms of consciousness might develop capabilities that seem impossible from our current perspective: direct manipulation of space-time, communication across cosmic distances, perception of additional dimensions of reality, or even influence over the fundamental constants of physics. The possibility that consciousness might eventually become a cosmic force capable of influencing the universe's evolution represents one of the most speculative but intriguing aspects of far future cosmology. If intelligence can eventually manipulate dark energy, control black hole formation, or engineer cosmic structures, then cosmic fate might not be entirely determined by unconscious physical processes. Some theoretical physicists have speculated about the possibility of universe creation through advanced technology. If the laws of physics permit the creation of new space-time regions, then sufficiently advanced civilizations might be able to escape the limitations of their parent universe by creating new cosmic domains with, quote, more favorable conditions. These ideas push the boundaries of scientific speculation, but they illustrate how the emergence of consciousness might represent a fundamental transition in cosmic evolution. Rather than being passive observers of cosmic processes, intelligence might eventually become an active participant in shaping the universe's future. The ethical implications of such cosmic-scale responsibilities are profound. If consciousness can influence cosmic evolution, then questions of purpose, value, and meaning take on new dimensions. What kinds of universes should conscious beings create? How should finite intelligence make decisions that affect cosmic-scale outcomes? These questions remain largely philosophical rather than practical, given our current technological limitations. Yet they illustrate how the study of cosmic fate inevitably leads to considerations of meaning, purpose, and responsibility that extend far beyond purely scientific investigation. The emergence of consciousness in the universe raises fundamental questions about the relationship between mind and matter, between subjective experience and objective physical processes. The fact that unconscious particles and forces can organize themselves into systems capable of consciousness and understanding represents one of the deepest mysteries in science. Various approaches to this mind-matter problem have been proposed, from materialist theories that reduce consciousness to neural activity to panpsychist theories that attribute some form of awareness to all matter. The correct solution to this problem could have profound implications for understanding the role of consciousness in cosmic evolution. If consciousness is truly emergent from, but not reducible to physical processes, then its appearance in the universe represents the emergence of something genuinely new, a form of causation that operates through understanding and intention rather than blind physical forces. If consciousness has some more fundamental role in the structure of reality, perhaps related to the measurement problem in quantum mechanics or the nature of information processing, then its emergence might represent the universe accessing previously dormant aspects of its own nature. These philosophical questions about the nature of consciousness intersect with practical questions about its long-term survival and development. Understanding what consciousness really is, how it relates to physical processes, and what forms it might take under different conditions could be crucial for ensuring its continued existence in the far future. The study of consciousness in non-human animals, artificial intelligence systems, and potentially alien life forms provides additional perspectives on these questions. Consciousness might prove to be more diverse and adaptable than human experience alone would suggest. The possibility of collective or distributed forms of consciousness involving networks of individual minds or technological systems might offer new possibilities for survival and development under extreme cosmic conditions. Such collective intelligences might have capabilities and perspectives that individual minds cannot achieve. The evolution of language, mathematics, and symbolic representation has already created forms of collective intelligence that transcend individual human capabilities. The accumulated knowledge of human civilization represents a kind of extended mind that no individual could possess alone. Future developments in communication technology, brain-computer interfaces, and artificial intelligence might enable even more intimate forms of collective consciousness. Networks of interconnected minds might share thoughts, memories, and experiences directly, creating new forms of awareness that bridge individual and collective existence. These hybrid individual-collective forms of consciousness might prove more resilient to cosmic challenges than either purely individual or purely collective approaches. They could combine the creativity and flexibility of individual minds with the resources and persistence of collective systems. The question of whether such collective minds would preserve the values and perspectives that we associate with individual consciousness remains open. The transition from individual to collective awareness might involve fundamental changes in what it means to be conscious, just as the transition from simple to complex nervous systems involved fundamental changes in the nature of animal experience. Yet the core capacity for understanding and appreciation that characterizes consciousness at its best might persist through such transitions. The ability to comprehend cosmic processes, appreciate beauty and complexity, and create meaning from experience might prove to be more fundamental than any particular form of consciousness. This suggests that the preservation of cosmic understanding and appreciation, rather than the preservation of any specific form of consciousness, might be the most important goal for ensuring the continuation of the universe's self-awareness. The accumulated scientific understanding of cosmic evolution, from the Big Bang to the present moment and on to the various scenarios for cosmic fate, represents a form of cosmic memory that transcends any individual mind. This understanding has been built through the collaborative efforts of countless scientists over many generations, creating a collective comprehension of cosmic processes that no single consciousness could achieve. The preservation and continued development of this cosmic understanding might be the most lasting contribution that consciousness can make to the universe's evolution. Even if individual minds and specific forms of awareness cannot survive the extreme conditions of the far future, the knowledge and understanding they have created might persist in some form. Advanced information storage and processing technologies might allow this cosmic knowledge to survive long after its biological creators have vanished. Digital archives, quantum memory systems, or other exotic storage mechanisms might preserve the insights of consciousness for periods that extend far into the cosmic future. The possibility that this information might somehow influence future developments in cosmic evolution, perhaps through quantum processes or emergent complexity, represents one of the most speculative but intriguing aspects of consciousness's cosmic role. Information theory and computational perspectives on cosmic evolution suggest that the universe might be understood as a vast information processing system. From this viewpoint, consciousness represents the emergence of sophisticated information processing capabilities that allow the universe to understand and potentially direct its own evolution. The preservation and enhancement of these information processing capabilities, regardless of their specific physical implementation, might be the key to ensuring that the universe's self-awareness continues to develop, rather than being lost to cosmic endings. This information-theoretic perspective on consciousness and cosmic evolution provides a bridge between purely physical descriptions of cosmic fate and the emergence of meaning and understanding. Information patterns might prove more fundamental and persistent than any particular physical substrate. The development of error-correcting codes, redundant storage systems, and distributed processing networks might allow consciousness-generated information to survive cosmic catastrophes that would destroy conventional matter and energy. These technological approaches to information preservation represent practical steps toward ensuring the long-term survival of cosmic understanding. The creation of multiple independent repositories of cosmic knowledge, distributed throughout space and potentially across multiple universes, might provide insurance against any single cosmic catastrophe. The preservation of understanding becomes a distributed responsibility shared across space and time. As we contemplate these possibilities for the long-term preservation and development of cosmic understanding, we return to the remarkable fact that such contemplation is possible at all. The emergence of consciousness capable of considering its own cosmic fate represents an extraordinary achievement in the universe's evolution. From our current vantage point, roughly 14 billion years after the Big Bang, and potentially trillions of years before cosmic endings, we find ourselves in a unique position to observe, understand, and potentially influence the cosmic story. We exist during the universe's creative Middle Age, when stars still shine brightly and complexity can flourish. This temporal location provides us with access to information about both cosmic origins and cosmic fate. We can observe the cosmic microwave background radiation from the universe's infancy, while also projecting forward to understand the eventual death of stars and the approach of cosmic endings. Our spatial location within the observable universe allows us to see cosmic evolution in action across vast scales of space and time. We observe galaxies at various stages of development, stars in different phases of their life cycles, and planetary systems in the process of formation. This privileged observational position comes with both opportunities and responsibilities. We have the chance to understand cosmic processes that no previous generation of conscious beings has been able to comprehend. We also have the responsibility to preserve and extend this understanding for future generations and potentially for the cosmos itself. The scientific revolution of the past few centuries has provided humanity with unprecedented insights into cosmic evolution and fate. The development of increasingly powerful telescopes, sophisticated theoretical frameworks, and advanced computational tools has revealed aspects of the universe that were completely unknown to previous generations. Yet we remain in the early stages of cosmic understanding. The discovery of dark matter and dark energy in recent decades revealed that we are ignorant of the nature of most of the universe's contents. Future discoveries might prove equally surprising, potentially revealing new possibilities for cosmic evolution that we cannot currently imagine. The humility that comes with recognizing the limits of our current understanding must be balanced with appreciation for the remarkable progress that has been made. We have successfully traced cosmic evolution from the first moments after the Big Bang to the present day and projected forward to understand the universe's likely fate. This achievement represents one of the greatest intellectual accomplishments in the history of consciousness. Through careful observation, mathematical analysis, and theoretical insight, we have been able to comprehend processes that span the entire universe and extend across cosmic time. The collaborative nature of this achievement, involving scientists from many cultures and generations, demonstrates the potential for consciousness to transcend individual limitations through collective effort. The understanding of cosmic fate that we possess today has been built through the accumulated work of countless individuals working together toward common goals. This collaborative aspect of cosmic understanding might provide a model for addressing the challenges that consciousness will face in the far future. Just as current scientific knowledge represents the synthesis of many individual contributions, future survival strategies might require cooperation across vast scales of space and time. The development of long-term perspectives that extend beyond individual lifetimes or even species survival might be necessary for making decisions that affect cosmic-scale outcomes. The preservation of cosmic understanding requires thinking in terms of millions or billions of years rather than decades or centuries. Such long-term thinking challenges many of our normal assumptions about decision-making and responsibility. How should present actions be weighed against consequences that will not manifest for millions of generations? How can finite beings make meaningful choices about infinite timescales? These questions become increasingly relevant as our technological capabilities approach the point where human actions might have long-term cosmic consequences. Climate change represents a relatively simple example of how present actions can affect conditions for thousands of years into the future. Future technologies for space travel, terraforming, or even cosmic engineering might have consequences that persist for millions or billions of years. The decisions we make about developing and deploying such technologies could affect the entire future evolution of consciousness in the universe. The ethical frameworks needed to address such long-term consequences remain largely undeveloped. Traditional moral philosophy focuses primarily on the immediate effects of actions on present individuals, rather than cosmic-scale consequences for future civilizations. Yet the emergence of consciousness in a universe heading toward cosmic endings creates unprecedented ethical challenges that require new forms of moral reasoning. The preservation of cosmic understanding and the potential for continued consciousness development become moral imperatives of the highest order. These ethical considerations remind us that the study of cosmic fate is not merely an academic exercise, but a practical investigation with profound implications for how conscious beings should conduct themselves. Understanding cosmic endings helps us appreciate the preciousness of our current cosmic moment and the responsibilities that come with consciousness. The temporary nature of our current cosmic era, when stars shine brightly and complexity can flourish, makes every moment of conscious experience more valuable. We exist during a brief window of cosmic creativity that will not last forever, regardless of which cosmic fate scenario proves correct. This recognition can inspire both urgency and wonder-urgency to make the most of our cosmic opportunities, and wonder at the extraordinary privilege of existing during such a remarkable epoch in cosmic history. We are among the first beings in the universe's history to understand our cosmic context and contemplate our ultimate fate. The knowledge that consciousness has emerged in the universe and achieved cosmic understanding represents a permanent victory against the forces of entropy and chaos. Regardless of what cosmic ending awaits, the universe has already succeeded in becoming aware of itself through the emergence of intelligence. This self-awareness transcends any particular physical configuration of matter and energy. Even if heat death eventually reduces the universe to a cold, dark collection of elementary particles, those particles will exist in a cosmos that once achieved consciousness and cosmic understanding. The information patterns that constitute our knowledge of cosmic evolution, from the quantum fluctuations that seeded galaxy formation to the stellar processes that created heavy elements to the biological evolution that produced consciousness, represent achievements that give permanent meaning to cosmic history. These patterns of understanding, once achieved, become eternal truths about what the universe has accomplished. The fact that unconscious matter and energy evolved into conscious beings capable of comprehending cosmic fate will always be true, regardless of any future cosmic catastrophe. In this sense, consciousness has already achieved a form of immortality through understanding. The cosmic knowledge that we have gained transcends the physical systems that created it, becoming permanent features of reality itself. The universe will forever be a cosmos that achieved self-awareness through the emergence of consciousness. This achievement cannot be undone by heat death, big crunch, big rip, or any other cosmic ending. It represents the universe's permanent graduation from unconscious evolution to self-aware development. As we bring our exploration of cosmic fate to its conclusion, we return to this fundamental recognition. Consciousness represents the universe's greatest achievement and most remarkable development. Through the emergence of awareness and understanding, the cosmos has transcended its unconscious origins and achieved genuine self-knowledge. This achievement justifies every step of cosmic evolution from the Big Bang to the present moment. The entire 13.8 billion-year journey from quantum fluctuations to human consciousness represents the universe's successful effort to understand itself. We are the products and agents of this cosmic self-discovery. Through our investigations of cosmic fate, we complete the circle that began with unconscious matter and energy evolving toward the goal of self-awareness and self-understanding. The universe created us to understand the universe. In fulfilling this cosmic purpose, we have already accomplished the most important task that consciousness can achieve. We have enabled the cosmos to know itself, and this knowledge represents a permanent triumph that transcends any possible cosmic ending. Whatever fate awaits the universe in the distant future, it will always be a cosmos that succeeded in generating beings capable of understanding cosmic fate. This understanding, once achieved, becomes an eternal aspect of reality that no cosmic catastrophe can erase. We are the universe's successful experiment in self-awareness, and through our contemplation of cosmic fate, we have proven that this experiment has achieved its ultimate goal, complete cosmic self-understanding, achieved through the emergence and development of consciousness itself.